Look at any machined part. To the naked eye, it seems smooth, but zoom in and you'll find a hidden landscape of microscopic peaks and valleys. This is surface texture, one of the most critical yet misunderstood aspects of engineering design. It's not just about looks. Surface texture controls how parts wear, seal, hold lubricant, and even how they're painted. The right texture can mean the difference between a bearing that lasts a million cycles and one that fails in days. In this video, we'll break down the essentials: roughness, waviness, and lay. We'll decode parameters like Ra and Rs and show you why they matter. You'll learn how to read and specify surface texture on engineering drawings using ISO and ASME symbols. We'll connect these specs to real-world applications, seals, bearings, and cosmetic finishes. We'll also cover common mistakes that lead to costly failures and give you a practical checklist to avoid them. Whether you're an engineer or a manager, you'll gain the confidence to specify surface texture with precision. Stop seeing surface finish as a footnote. Start using it as a lever for performance and quality. Ready to unlock the power of surface texture? Let's get started. What is surface texture? It's the collection of tiny deviations from a part's ideal surface, created by every manufacturing process. Engineers break it down into three main components: lay, waviness, and roughness. Lay is the dominant direction of the surface pattern. Think of wood grain or the lines from a lathe. Lay matters because it affects friction, fluid flow, and even how light reflects. Waviness is the broader, gentle undulations caused by machine vibration or heat treatment. Excessive waviness can create leak paths, even if the surface feels smooth. Roughness is the fine, high-frequency irregularities left by the cutting tool or abrasive. Roughness impacts friction, wear, lubrication, and fatigue life. Too rough, and you get abrasion. Too smooth, and you lose oil retention. Most surface parameters, like Ra and RZ, describe roughness. Understanding lay, waviness, and roughness is the foundation for smart design. Get these right, and your parts will perform as intended. Surface roughness is measured with parameters, each revealing something different. Ra, the roughness average, is the most common. It's the average height of peaks and valleys. But Ra alone can be misleading. Two surfaces can have the same Ra but very different profiles. RZ, the average maximum height, captures the distance between the highest peak and lowest valley, making it sensitive to outliers. RQ, RMS, gives more weight to large deviations, while RT measures the absolute peak-to-valley height. SM tells you the average spacing between peaks, fine or coarse texture. Advanced parameters like RSK, skewness, and RQ, kurtosis, describe the shape of the profile, important for oil retention or wear. Negative skew, RSK, means deep valleys, great for lubrication. High kurtosis, RQ, means sharp peaks, potential for scratching. Use multiple parameters to design surfaces for specific functions, not just for smoothness. The right combination ensures your part performs, seals, and lasts. Don't settle for Ra alone. Specify what matters. You can't control what you can't measure. The stylus profilometer is the workhorse, dragging a diamond tip across the surface to create a profile and calculate parameters like Ra and RZ. It's robust and reliable, but only gives a 2D slice, missing isolated defects. For delicate or complex surfaces, non-contact optical methods like white light interferometry create full 3D maps, capturing every detail. Use stylus profilometers for routine checks on durable parts. Switch to optical for soft, critical, or complex surfaces. Always match your measurement method to your part and note it on the drawing. The right tool ensures your specs are met every time. Measurement is as important as the numbers you call out. The engineering drawing is where your surface texture knowledge becomes reality. The checkmark symbol is the standard. Add numbers above it to specify roughness, usually Ra. For more control, stack parameters: Ra, RZ, lay direction, even the manufacturing process. Add a horizontal line to note the process, like grind or mill. Specify waviness or spacing to the left, lay to the right, and other parameters below. Be as specific as needed, but don't overdo it. Overspecifying drives up cost. For critical surfaces, call out multiple parameters and the measurement method. For non-critical areas, keep it simple. Clear, complete callouts prevent confusion and scrap. The right symbol tells the machinist and inspector exactly what you want. Good drawings make good parts. Surface texture isn't one size fits all, it's about function. Bearings need a smooth surface with enough valleys for oil, low Ra, negative risk. Sealing faces must be smooth enough to prevent leaks, but not so smooth the seal sticks. Ra and lay matter. Painted or coated parts need a roughness that gives tooth for adhesion. Too smooth and coatings peel. Threaded fasteners rely on controlled texture for consistent friction and preload. Each application has its own ideal texture. Match your parameters to the job. Don't just copy-paste values. Think about what the surface needs to do. The right texture boosts performance, reliability, and appearance. Specify for function, not just tradition. That's how you get parts that work. Once you've mastered the basics, you can fine-tune surfaces for even greater control. Profile tolerancing uses the Abbott-Firestone curve to define how much of the surface is plateau versus valley, ideal for bearings. Parameters like RPK, RK, and RVK let you specify peak, core, and valley depths for targeted performance. Surface integrity goes beyond texture. Manufacturing can introduce stresses, micro cracks, or hardness changes. For fatigue-critical parts, specify not just texture, but also process and verification of residual stress or micro cracks. Techniques like shot peening add beneficial compressive stress, boosting fatigue life. True surface engineering considers both geometry and metallurgy. For critical applications, go beyond raw. Control the whole surface story. That's how you design for durability and safety. Small mistakes in surface specs can cause big problems. Underspecifying, using a single Ra for every surface, ignores function and can lead to failures or unnecessary cost. Relying only on Ra misses scratches or outliers. Add RZ or RT for critical surfaces. Ignoring lay can cause leaks or wear. Always specify direction for seals and moving parts. Overspecifying smoothness wastes money and can hurt function. Don't call for a mirror finish unless needed. Every spec should have a reason. Justify it with function. Think about how the part works, not just how it looks. Avoid generic notes. Tailor specs to each surface. The right callouts save time, money, and headaches. Smart specs mean better parts. Before releasing your drawing, run a quick checklist. Have you specified texture for every functional surface? Seals, bearings, coatings. Did you avoid overspecifying non-critical areas? Are your parameters complete? Ra, Rs, lay, process, where needed. Is your spec manufacturable and measurable with available tools? Did you note the measurement method and cutoff? Every surface spec should be deliberate and justified. A few minutes of review now prevents costly mistakes later.